Now, let us describe the dual spaces for the Lebesgue space LP in the extreme values of P. That is when P is equal to 1 and P is equal to infinity. So in fact, for P is equal to 1, the Rees-Fisher theorem is also valid. So let us state that as our first remark. So this is also valid when P is equal to 1. In this case, the map J from, so the dual exponent of 1 is infinity. Into the dual of the Lebesgue integrable functions. So we have the same mapping. So this is defined as the integral of the product. Now for all f in ln L1 and g in L infinity. This is an isometric isomorphism. And the proof is very similar to the one that we established, but of course we need to be very careful in some parts, namely the use of the Rees-Fisher Rees theorem. Okay. Nevertheless, the proof here can be found, for instance, in the book of Alt. So we will not proceed with the proof. Basically, the proof is similar to what we have established, but with a few modifications, of course, to fit to the case when P is equal to 1 and Q is equal to infinity. Now, how about for the other extreme case? That is when P is equal to infinity. Well, the dual of L infinity is somewhat complicated. Okay. More precisely, it consists of measures. And this is possible for, let's say, a locally compact topological space. By this, we mean that any point is contained in a compact set. And X sigma mu is also a sigma finite measure space. Then the dual of L infinity is symmetrically isomorphic to BA of X. And what is this BA? BA of X is defined to be the set of all measures, nu, side measures, okay, wherein nu is additive and nu is absolutely continuous with respect to mu, and it has a finite total variation, okay, with the following norm. Okay. So the norm is the total variation norm. And it can be shown that this is indeed a Banach space. And this the space of additive and absolutely continuous side measures with respect to mu having a finite total variation is the dual of L infinity up to an isometric isomorphism. And here B and A are the first letters of the word bounded and then additive. So you have here additivity. Here it means that your total variation is bounded. So in fact, one can provide an isometric isomorphism. So the map J from BAX into the dual of L infinity. So let us take a function G in L infinity, or I should say a measure nu, bounded and additive. Okay. So it's in BAX. So we need to have a function in L infinity. So let us say my argument is F. So F is essentially bounded. Then we take the action of J nu at F. So we integrate F with respect to the measure nu. Okay. So this map is an isometric isomorphism. So the proof is quite technical. You can look at the book of Danford and Schwartz. So here we are only stating the duality with respect to some isometric isomorphism, and the proofs are located in these references. Due to the limited time that we have, of course, we will not prove these remarks here. Okay. So if we have this dual, okay, or this is now the dual of L infinity up to an isometric isomorphism. So the case where P is equal to infinity is a bit complicated because it consists of signed measures. In particular, additive signed measures that are absolutely continuous with respect to mu and has a finite total variation. So to characterize the dual spaces of the space of continuous functions, okay, and continuous functions with compact support, let us consider a subset S in Rn, okay, with respect to and provide this with the relative topology. Okay. We define RCA of S, okay, to be the set of all measures, let's say nu, on the Borel sigma algebra on S. So this is the restriction Borel sigma algebra into R. So these are the set of all measures. So nu is a sigma additive. It has a finite total variation, and nu is regular. So here, what do we mean by nu being a regular Borel measure? So this means that for any A in the Borel sigma algebra of S, the infimum of the measure of the difference, let's say O minus C, where O is open in S, C is closed in S, and C is a subset of A is a subset of O. Okay. This one is equal to 0. So this is regularity. And take note that one can, in fact, show that this is equivalent to the following statement, that the measure of A is the same as the infimum of the measure of O containing A, O open in S, and this is the same as the supremum of mu of C contained in A, C close in S. Okay, and one can replace here the criterion that C is close by C to be compact. Okay. So RCA refers to regular countably additive measures. So sigma additivity or countable additivity. So that's the space of measures, regular countably additive measures having finite total variation. So with this, we can now state the so-called Riesz-Radon theorem. That characterizes the dual of a space of continuous functions on a compact set in Rn. So you take K to be S in the previous example. Then the dual of the space of continuous functions is isometrically isomorphic to the space of regular countably additive Borel measures in K. More precisely, the map. Okay, let us denote it by J again. So the map J from RCA to the dual. Okay, given by, okay, so J, I take a measure, regular countably additive measure in K. So this must be in the dual of CK, so the argument here must be in CK, continuous on the compact set K. So we integrate F over K with respect to the measure nu. This one is an isometric isomorphism. Again, you can define a norm on RCA that makes it a Banach space using the total variation. This is finite due to the assumption. So I think there's a typo here. This must be S. So the space of the dual of the space of continuous functions is also a bit complicated. It consists of measures, in particular regular countably additive measures having finite total variation. Replacing the compact set by an open and bounded set yields the Riesz-Markov theorem. By the way, for the proof of the previous one, you can look the book up. So as I said, replacing the space of space K or the subset K by an open and bounded set. So that's let us change notation. Okay. Be let's say open and bounded. We call that C naught omega is the space of all functions that are continuous in omega with a compact support. So then we also have the following similar duality. Okay, so the dual space of C naught, okay, is also the space of regular countably additive measures in omega. And the analogous isometric isomorphism is similar. So now instead of space of continuous functions on a compact set, here we have a continuous function in an open and bounded set, but zero outside a compact set. So basically, you prove this using the Riesz-Radon theorem. So again, the map J is defined in this way. But now F is in C naught omega. So the same definition for J, but you need to replace the function F and then the domain K by omega. So again, this is an isometric isomorphism. The proof can be, for instance, can be seen in the book of Rodin. Or you can use the Riesz-Radon theorem and the Hahn-Banach theorem. So extending a function in C naught omega to its up to its closure. So that's an alternative proof. Or probably that's the proof provided in Rodin. And finally, okay, so now we know that the dual of CK or C naught omega consists of regular countably additive measures. We would like to ask, how about the dual of RCA? And for this, let us consider a subset S in Rn. And suppose that this is either compact or a bounded open set. So the compactness of S would be related later to this the dual of RCA. when K is compact. When S is omega and bounded, you can take S to be omega, and we want to study the dual of this case. So this statement will cover the case of the Riesz-Radon and Riesz-Markov theorem, in particular the RCA space. Now we define the following space. So L infinity RCA S with values in L infinity S. So here the Borel sigma algebra is the Borel sigma algebra in S, and we take the Lebesgue measure. So this is the set of all functions, let's say f from RCA into L infinity, such that f of mu is equal to f of nu. So these are L infinity functions, okay? Mu almost everywhere, whenever mu is absolutely continuous with respect to nu. And we define the norm as follows. So this is the sup over all nu in RCA of f of nu. This is now in L infinity S. So this function space consists of functions defined on RCA into L infinity of S. Then the dual of RCA of S is isometrically isomorphic to this complicated function space. And in fact, we can construct an isometric isomorphism. So the map J from L infinity RCA of S to L infinity of S into the dual of RCA, okay, given by. So here we take a nu I should say we take an f, and we evaluate with respect to nu. So f here is in L infinity RCA of S, L infinity of S, and nu is a regular countably additive measure. So we integrate this over S f of nu d nu. Now take note that this is an element of L infinity. Okay. Of S. So this is also an isometric isomorphism. So the dual gets complicated for the case of regular countably additive measures. And those who are interested with the proof, you may consult the book of Conway, for instance. So that's the dual, some dual spaces. And we only stated them without proof, but to those who are interested in the proof, you can consult the book of Alt the book of Dunford and Swartz, the book of Rodin, and the book of Conway for the proof of these statements or these remarks. And that's it for the dual spaces of these concrete function spaces. In the next lecture, we will discuss further theorems related to the bare category theorem.